Thank you, Denise. Hello, everybody. Welcome to another live keynote session at ONF Spotlight event on 5G transformation with open source. Today, you will hear exciting keynotes around the general themes of disaggregation, virtualization, distribution, and SDNization of the mobile networks for 5G. My name is Oguz Sunay. I'm the VP of R&D for Mobility at ONF. I'm very excited to introduce today's speakers. Alex Choi is someone I have known, followed, and admired for a very long time. He's truly a visionary, and he has consistently brought in significant transformation to everywhere he went, and is continuing to do so. Alex is the Senior Vice President of Research and Technology Innovation at Deutsche Telekom, where he leads efforts on 5G and Edge. He's also the head of T-Labs. He also serves as the operations officer at O-RAN Alliance. Prior, Alex was the CTO of SK Telecom, and he was also the founding chairman of TIP. John Smee is an old friend of mine. We were graduate students at the same time. John has always been stellar at research and innovation. He's currently the VP of Engineering at Qualcomm, where he oversees all of Qualcomm's 5G research activities, all the way from design and development of new chipsets to building new prototypes around them. And last but not least, Larry Peterson is one of the reasons why I wanted to come and work at ONF in the first place. He's a legendary researcher. He is the CTO at ONF and an authority in systems and platforms. Some of you may have used his book on computer networks as the textbook for one of your courses. Prior, Larry was a professor of computer science at University of Arizona and Princeton, and the director of Planet Lab. He also co-founded a startup to commercialize CDN on Planet Lab, which was subsequently acquired by Akamai. Larry is a recipient of the prestigious SIGCOMM Award, as well as the IEEE Kobayashi Award. He is a member of the National Academy of Engineering. So with that, I welcome all three, Alex, John, and Larry. I look forward to your keynotes. Larry, take it away.
Okay, thank you. And hello, everybody. So what I thought I would do today is talk about, I always mentioned platform, and what I wanted to do is to talk about what's happening in 5G from a platform perspective. And in particular, at ONF, we have been spending a lot of time for the last several years pursuing an agenda having to do with SDN, making the network programmable. So while open source is clearly a critical ingredient, it's also, I want to set the bar a little bit higher and talk about the SDN principles that we can bring to bear and are at ONF bringing to bear on 5G. So what that involves here is I'm going to start with a little bit of an SDN journey just to refresh everyone's memory as to what the highlights are and what's important about SDN. And I think that the biggest way to, most important way to look at that is really about taking what both in certainly networking, but prior to that in computing, were closed and proprietary systems. They were bloated and complex, had lots and lots of functionality bundled inside of them. And there was not a huge incentive to improve. And that left us both years ago in the computing industry and a bit more recently in the networking industry with networks that were hard to manage, hard to secure, and hard to change. The promise of SDN is that we can, by opening up some interfaces and transitioning from proprietary closed systems to commodity hardware, white box switches, running software that controls them on commodity servers, we can build systems that are from merchant silicon, involve open source, and critically can adopt cloud practices. And that's kind of what brings us to the notion of platform, that we're bringing the best of the agility of building cloud systems to the network. And so that results in networks that are hopefully going to be easier to fix and repair, diagnose. It's going to be faster for us to innovate, and they're going to be simpler to operate. And that's kind of linked to it's a platform, and we're adopting best practices in building clouds. So that's the promise of SDN. That's the agenda that we've been pursuing, and we have seen dramatic transformations throughout a lot of the networking industry. It's not a journey that's finished yet. There's still work going on in progress. And I wanted to draw attention to one of the most exciting things that's happening in the SDN space, which is the transition from the hardware, those merchant silicon chips that were built into the white box switches, transitioning from having a fixed processing pipeline where we knew what the header was going to look like and what fields that we were going to do matches on and forward packets on, to a more programmatic environment where the switches are themselves in the data plane now programmable. And so instead of having a fixed set of tables that we're doing lookups on, we have programmable match action pipelines and load into that hardware a P4 program. If you're not familiar with P4, I strongly encourage you to go look into it. But basically, it is, think of it as a restricted version of C that lets you say how I'm going to deal with packets that come through the data plane of in the forwarding plane of my network. So not only then do we have open source and programmability at the control plane, but we are now in the process of moving that ability to decide how packets are processed into the forwarding plane, into the dating plane of the switches. Now, that's what SDN is about. So what happens next? What is exciting about that capability that we hope to then also apply to the 5G case? Well, in short, where this brings us is that we now have the ability to program the network both end to end, from source to destination, and from top to bottom, from the control plane all the way down into the data plane. And a big part of that, of course, is that we have now P4 programmability both in the switches and in the NICs, the smart cards, the smart NICs that are connected into the servers at the edge, and in the virtual switches as well that might process packets and forward them onto virtual machines. We also have a lot of exciting open source happening to optimize the path that the packets follow through the server, both in the kernel stack and up into user space. On top of that, then, we now are building the SDN controllers and the SDN applications that can control that network. So now this is both the end-to-end and top-to-bottom part of the story. End-to-end, it's all the way from the virtual switches to the NICs to the switches on the end-to-end path. And we were able to, through open source software, write the programs that control the switches and the forwarding software that runs inside of the switches. So what is that good for? Well, one of the things that this opens up for us is the ability to specify the behavior of our networks in a very top-down sort of way, and to automatically compile and partition all of those components and then install them into the underlying hardware. This gives us the ability to construct exactly the network that we want deployed for our users. So we now know, because we're the ones that specified as the network operator, we're the ones that specified the behavior, that we have correctness by construction of this network. So that's the first big thing that's going to come from this change. The second thing has to do with visibility into what's happening inside of the network once we have programmed it by construction, and being able to verify that in fact it is behaving the way that we wanted it to, and if it should ever deviate from that, we have the ability to correct it. So one of the key ingredients of this is the ability to do fine-grained network telemetry. In-band network telemetry, INT, is the technology, but it's basically programs implemented in P4 running in those switches and smart NICs and virtual switches end-to-end, collecting information about what's happening with the packets as they're passing through the data plane. We can check to see that how long they're being queued, who they're being queued behind. We can determine which rules in our forwarding tables were the ones responsible for the packet being forwarded. We can in fact verify them that the packet is being processed exactly the way that we want it to. And what basically comes out of this telemetry then is a set of basically a trace of what happened to the packet. And we can feed those traces into a verifier. And again, check these traces by the verifier against the high-level specification, and either verify that the network was behaving exactly the way we wanted it to, or that some corrective action might need to be taken. And of course, the last step is, if we do decide that action needs to be taken, we now have the ability to close the loop and come back in and take corrective action through the top-to-bottom pipeline, the top-to-bottom control that I was talking about a minute ago. So now think about this for a second. It's not just that we had open source that was an absolutely critical ingredient, but it's also because we've constructed the network we specified the network's behavior top-down ourselves as the network operator, and we can watch what happens inside of the network and verify that it's behaving the way we intended to, that we now have full control over our network. This is the promise that SDN is bringing, and it's the one that I wanted to talk about now in the context of 5G a little bit more. So this is the end-to-end, top-to-bottom programmability picture. It's going to allow networks for the first time to be programmable end-to-end, specified top-to-bottom, defined entirely in software. This creates the possibilities of verifying networks correct by construction. We can measure and validate in real time against the specification, and we can correct bugs. That's the value that we're bringing. So the question is, what happens when part of our network end-to-end is now the 5G mobile network? And that's what I want to spend the rest of my few minutes talking about. The details are going to change, of course. The way that the control programs that I use to control the 5G mobile network will be different. They will be having to do with handover control and link aggregation and load balancing and slice management and so on, as opposed to a re-implementation of BGP, but it's basically going to be the same model. This is all possible because of the transformation that we are focused on here today, which is the transformation of this proprietary, bundled, closed system into one that is, in fact, much more disaggregated and open. And so let's just look at that transformation for a second, just to appreciate all that is going on. We're breaking out the radio unit, distributed unit, the central unit. This is the specification that comes out of the O-RAN Alliance as to how to split the RAN. We have components then exposed and visible to us in the core. And in fact, the bottom line is, if we do this correctly, we will end up with an open sourced and microservice-based end-to-end collection of disaggregated units that implement the 5G network in exactly the same way we were talking about with the wired network just a minute ago. Now, that's the critical first step, but we want to do a little bit more than that. And so let's see how that all plays out. And this is now how we're going to transform this opportunity into the end-to-end and top-down programmability that I've been talking about. So the first thing is we take what used to be a piece of control functionality that was embedded in the central unit, and we elevate that out and make it an SDN controller. And that controller controls both the central unit and the distributed unit. And this is where we run the set of applications that I was talking about a minute ago that really are in the sweet spot of what SDN is all about. Because one of the promises of SDN is that we've taken functionality that used to be distributed across all of the individual subsystems, whether they be switches or the radio units, making a locally optimal decision. We aggregate that information back into a global, logically centralized place so that we can make the globally optimal decision. And then we push the results back out to the individual units. That's exactly the scenario going on here with functionality like handover control and load balancing and so on. Now, of course, there are other levels to the stack. There is a management plane that sets the policy, for example, how resources will be divided between different slices. But if you stand back and look at this picture for just a minute, this is exactly the top to bottom control that is necessary to give the operators of these networks complete control over their top-down control over their networks. And I just wanted to highlight the critical pieces of this. Really, this network is a set of, turns out to be a set of control loops. We have a non-real-time control loop that sets the policy. That policy gets pushed down to the next control loop, which is near real-time. In 5G terminology, this is the RIC. But if we think of it as an SDN controller, it has, in the 10 millisecond control loop range, the ability to control the subsystems underneath it. And I didn't call it out in my picture earlier, but of course there is one much tighter control loop running down. It is the scheduler scheduling the spectrum. But this is a control loop that also is made visible to us, and now top to bottom we can completely control our network. So again, it's the point I'm trying to make here is open source is obviously critically important. It's a necessary ingredient, but it's how we organize and take advantage of that open source that's going to ultimately give us the control over the networks that we want. Now, there's another ingredient to this, which is, this is the control plane. What about the data plane? Well, we also have the opportunity to take advantage of the same programmability that we saw in the in the wired network, and it's being used in both WANs and in data centers, and apply it to the user plane or the data plane here in the 5G network. And so I'm calling attention to a couple of the submodules here, one of them in the core and one of them in the central unit. And this is still very much work in progress, but I wanted to point to the potential of this and just give you a sense that this is something that is coming and that we're working on. And so in particular, in a couple of slides here, I want to just focus in on the user plane function of the NG core. And some work that we're doing at ONF with other partners, including Intel, to program that in P4. So let's take a look a little bit at what that looks like. So I'm going to blow that UPF up and take a look at what's inside of it. And the short answer here is that it certainly is a combination of software components and hardware components, and those hardware components are programmable. So the first thing, again, the UPF is sitting on the user plane between the radio unit and the rest of the internet. There is a programmable switch, and that is where part of the answer is going to be, solution is going to be implemented. In addition, then we will have a set of smart NICs and servers and virtual switches and the agent that talks up the control plane. So let me just kind of describe this figure before I move on. I'm not focusing now for the moment on the control plane, except to point out that it is certainly there, and there's a piece of the connection of that control plane running on the server. But it's a combination of the programmable switch, which is now we're using Tofino switches from Barefoot that are P4 programmable. We also have a combination of dumb NICs and smart NICs, but those smart NICs are another example of a P4 programmable device. And in the case where we choose to build this out of regular NICs, we are going to put the intelligence into the virtual switch, also in principle controllable via P4. So now we've recreated exactly the scenario that we were looking at before in the wired network, that we can, through correctness by construction, build out a UPF that behaves exactly the way that we intended it to. Now, the devil is in the details, and there are some non-trivial details here that I want to point out. So the first one, basically, we're working on currently two different paths through this combination of hardware. The first path, let's call it the software path. Packets flowing between the internet and the radio unit will first hit the programmable switch, of course, and then get passed up to the NIC, which will pass it up to the V-switch. The V-switch will do whatever work needs to be done there, and I'll come back in a minute and talk about how work gets split between the software side and the hardware side. But we'll do whatever needs to be done to the packet to implement the UPF functionality and then forward it back through the switch off to the internet and vice versa in the other direction. The second path that we are working on, we call it the hardware path, never has to touch the server. Basically, the switch receives the packet, passes it up to the smart NIC, and the smart NIC is able to implement the rest of the functionality that was required to process the packet and then forwards it back out. Now, you might be asking yourself, why didn't everything get done in the programmable switch? That was what happens in the data center. And the answer is that programmable switch doesn't today have quite everything that we need from it, but we would anticipate that over time it will. And in fact, it's probably going to be the case that it's a combination of different kinds of computing units, whether it be a unit that had a switching chip in it or a unit that had a general purpose processor in it, that needs to be processing the packet. And this, in fact, is a critical part of the notion that there's a platform here. We have a collection of commodity components below us. But in general, some of the QoS work and buffering that has to happen during the time that the user is moving from one base station to another is currently handled as a combination of vSwitch and NIC in the one case, or the smart NIC in the other example. And it's the tunneling termination that's being handled down in the programmable switch. And that's a function of the programmable switch today not having sufficient buffering, although over time, again, those situations could change. And in fact, I think that's one of the more interesting open questions here, is how much of this functionality can ultimately be pushed down into the programmable switch as the 5G use case becomes a critical and important one for this segment of the industry. So I think the big picture here, which I want to kind of end on, is we are moving into a regime where we have a variety of commodity and programmable hardware sitting below us. And we have microservices, small disaggregated functionality implemented in software up and down the stack. And it's that combination that turns the network into, including now, in potentially here, the 5G parts of the network into an end-to-end controllable platform. And it's, again, circling back to the notion that the cloud was a critical, that bringing cloud practices was a critical part of this. We now have the ability to innovate very quickly, and we have feature velocity because we have the ability to push the software where it needs to be and update the software over time. That this is the really exciting opportunity that comes out of the work, the fact that the 5G network is being opened up and being transformed into an open source paradigm. And so with that, I believe I will stop and turn it back over to you, Oz.